Hi, welcome to Mindset. Today we're doing Physical Science Grade 10 and specifically scalars and vectors. Now, I'm quite sure you've heard of these terms, scalars, vectors. What's the difference between them? Well, we're going to find out in just a moment. Let's have a look at the lesson outline. Here it is. Vectors, scalars, compass bearings. Why compass bearings? Because compass bearings tell us about direction. And as you probably know already, vectors have something to do with direction, or direction has something to do with vectors. Graphical representation, well, that's just a fancy term for drawing on a piece of paper, showing pictures of things like vectors. And resultant vectors, there's a term you may not have come across before. Resultant is simply a vector sum. Okay, but we'll get onto that in more detail in just a moment. Let's have a look at our key concepts. I'm going to use terms like quantity, and I'm not just talking about how much of something there is. I'm talking about a quantity like mass is a quantity. It is something that tells us something about a property of matter, for instance. A quantity like velocity is something that we use to describe a certain state of affairs. In the case of velocity, of course, in the movement of a body, we can use a quantity like velocity to tell us more about how that body is moving. Obviously, again, a key concept, direction. I've gone on about that before. A term that is often used, which you'll see quite often related to vectors and scalars, is magnitude. It just really means size. It's the same thing. Magnitude, though, fancy word for size. How big is something? We talk about perpendiculars, as you know from your geometry. That's to do with right angles, and whenever we talk about right angles, lurking in the background somewhere is Pythagoras, Pythagoras' theorem. We know that, and we'll deal with it today. Parallels, yeah, well, that's very important. You know something about parallel lines, scalars and vectors. Well, those are key concepts which I've spoken about already. Let's just have a look straight away at scalars. Now, scalars. What does the word sound like? It sounds like scale. Nothing to do with fish, but certainly to do with scales. Okay? Things like that balance things. Now, it's nothing to do with balance as such, but a scale isn't just something that tells us whether one thing has got the same weight or has the same amount of mass in it as the other. But we can actually measure on a scale how much mass there is. And it's the measurement idea of scale that is very important. These quantities, scalar quantities, have no direction. Direction is not important. They have only size. So we can't use direction to tell us anything more about a scalar. All we can tell you is how much of it there is. And it is measured on a scale, and what's important about measuring things on a scale is that to measure scalars, we are going to use particular units. And the unit is going to be what describes that scalar. It tells us what scale we measure these things on. So let's have a look at some of them. Something called the SI unit, Système International. It's an authority based in France, and there we will get this system of international measurements, so that when we measure mass, when we measure length, when we measure time, we're all using the same units, and we agree with it. And that is the international agency that regulates the fact that when they talk about mass in China and they talk about mass in Botswana, they're talking about the same thing. This can be extended. Length, we use the term distance quite a lot, and we'll use that again today, and you'll see what that means. We derive from these basic units certain other units. For instance, when we take length in one direction and length in another direction, we can use that to describe area. And the units of area are not just meters as in length and distance, but square meters. Similarly, we can define volume, very important when we're talking about liquids and containers with liquids in them and how much of a liquid we have. We describe it in terms of a volume. Now, the SI unit for volume is cubic meters. However, if we talk in chemistry, we talk about cubic decimeters, a decimeter being 1/10 of a meter, and a cubic decimeter is therefore 1,000th of a cubic meter. Now, there's one group of scalar quantities that I want you to pay particular attention to. These are to do with energy and work. Anything to do with energy, anything to do with work, in fact, anything that is measured in joules or units of heat is a scalar. Now, you might find this a little odd, because we sometimes talk about close the door so we don't let the heat out or don't let the heat in. That's just the way we talk. It's not very good physics. But even if you may get heat moving from a colder body, from a warmer body to a colder body, that is not regarded as a direction in the sense of a vector, because regardless of where the other body is, a warmer body will always dissipate its heat towards colder places. And it's not one specific direction, which is what differentiates vectors and scalars. Vectors have got a particular direction. Time, we talk about the direction of time. Time is a scalar quantity. It doesn't have direction except for poets. We talk about the way time moves on and all of that sort of thing. It doesn't mean that time has a direction. Okay, so please remember anything to do with energy, and here we go. Now, what I'd like to do is just to show you very quickly a scale, what we mean by a scale. Let's take a temperature scale. Now, we've got 3 temperature scales that we can talk about, and to define a temperature scale, we take 2 natural events that are the same everywhere. And that is, let's take the melting point of water and the boiling point of water. We know that the melting point of water is at 0 degrees and 100 degrees on a particular scale, and that would be Celsius, the Celsius or centigrade scale. There are others. There's the Fahrenheit scale, which has melting point of water at 32 degrees, boiling point at 212. But they define that scale. You can see the size of a degree here is different from there. There is another very important one for science as well, and that is Kelvin, and that is K. And that has the melting point of water, or the freezing point, at 273 K, and boiling point of water at 373 K. Important thing about this thing is when we get down to 0 K, we have got what is called absolute zero. And there is a scale for you. Now we must move on and talk a bit about vectors. Vectors, of course, do have magnitude and direction. They're actually a scalar with direction, if you like. And we get very important ones, things like force, you've all heard about that, and velocity, you've all heard about that. Forces have units of newtons, and of course there's something called weight, which we'll talk about a bit more as well. Velocity has units of meters per second, and we can also write that meters per second. There's a funny thing here called displacement, which looks very like a distance, except that it's a distance with a direction. So it's got units of meters, just like distance, but it also has a direction. Other units, acceleration, momentum, we'll talk about these things later. And just remember that all of these things down here are crossed out because energy, temperature, heat, work, time, etc., none of those have directions. Okay, let's represent vectors. Here, I've got a representation of a vector. It's an arrow. It's an arrow which has a length. The arrowhead shows a direction. Now, if I take another arrow, you'll see that those two arrows are not the same length. If they were representing the same vector quantity, that would be a bigger whatever than that. If they were representing forces, that would be a bigger force than that, because it is represented by a longer line. And if we take any quantity where direction is important, and of course force is important, it's important to know whether it's pushing like that, or pushing like that, or pushing like that, because all of those forces have different effects. And the harder they push, the more we've got to represent that by a longer line. And a small force would be a shorter line, and the direction too is important. Okay, so now you know how to represent vectors. I'm just going to give you a very quick 30-second test. Just think of, or write down as quickly as you can, as many scalars and vectors as you can. Come on, you've seen it, go for it. Okay, the answers. How well did you do? Take a look. Scalars. We've got mass, we've got length or distance, we've got time, speed, area, volume, temperature, energy, work. All of those with joules, measured in joules. Vectors. We've got a force. Direction's important. Weight, usually pointing downwards. A displacement is like a distance with a direction. Velocity is like a speed with a direction. Momentum, something to do with mass and velocity. Acceleration, well, we'll talk about that in a later lesson. And then we've got a couple here that you'll come across in grade 11, which is electric field strength and magnetic field strength. Electric force, magnetic force, and how strong they are. I just want to pay attention to two in particular because they are very often confused. Mass and weight are related, but they are not the same thing. Mass tells us about the amount of matter in an object. An object's mass remains constant regardless of where you are in the whole universe, because it doesn't matter where you are. The amount of mass, it happens to be your mass, the amount of matter inside of you stays the same. It doesn't change wherever you go. However, when you talk about your weight, if you go to the moon, the people that have been to the moon, their weight was about 1/6 of what it is on Earth, because the pull of the planet, or the celestial body in the case of the moon, which is not a planet, the pull on anything close by to it is known as the weight. So your weight here on Earth, which you can measure on a scale, by standing on a scale which has got springs in it, which will extend more or less depending on if it's somebody smaller than me standing on it, or if it's me standing on it, I'll push that thing down to about 110 kilograms. You might be a smaller mass, and therefore your mass will be attracted towards the Earth with a smaller force. That's the weight that we talk about. So just remember that weight is the pull of a planet or some other body towards its center. Weight depends on the mass of the object, but they are not equal. They're not exactly the same thing. They depend on one another. And the weight differs according to the mass and size of the pulling planet or body in the case of a moon. Mass and weight, you've got the difference? Good. Let's take a short break.